So, welcome back to this course, Professional Scientific Communication. In this lecture, we are going to look into as to how you develop hypothesis, right? So, what is shown on the slide is the two distinct way of reasoning, meaning observing something and making a meaning out of it. The one that is shown on the right side is called as inductive reasoning. You observe something, from your observation you find that there are patterns. Based on the patterns you develop an hypothesis, and then you evolve what is called as a theory. Okay? So, this is one way of doing science, by looking at certain patterns from the observations that you have made. So, when you observe in this particular aspect, what you call the inductive reasoning, you really do not have a preconceived notion as to what you should look or what possibly it means. You only observe everything that is there and see is there any patterns, and whether the patterns mean something. Then you develop an hypothesis which may be true, which may not be true, but it's convincing. So that's what called as inductive reasoning. There is a different school of thought, although now you don't call it as a different school of thought. We'll try to bridge these two a little later, but a different school of thought is called as deductive reasoning, meaning you have a theory which is either proposed by you or proposed by somebody, or you looked at the literature, you come up with a kind of a theory, and you develop a hypothesis for your research project, a thesis, whatever. And then based on the hypothesis you do certain experiment to test the hypothesis, to validate the hypothesis, and you have an observation, and then you confirm that your hypothesis was right, therefore these are facts, right. So, from theory you sort of confirm. Another thing, you have observations to upfront you start with, and then come up with certain theory. So, these are possibly two distinct school of thoughts if you really look in that perspective, but may not be so in the long run. I will discuss a little later. Let us look into this inductive reasoning. For example, this kind of patterns that are very common in most of the exams that you probably would be attending. You basically look at as to what should be the next pattern that should be there on the fifth square that is now marked by a question mark, right. You know that by looking at the pattern, it looks like that hourglass is rotating. Therefore, what you expect is something what is shown on the very first square. It should be repeated. So, this is inductive reasoning. By looking at patterns, you infer something that is called as now hypothesis or theory. So, you can apply very similar thing to little more complex. For example, here there are different symbols, each one whether it's filled or unfilled. Then there are different combinations that are there. So, you have to look at how the square one changes in the square 2, 3, 4 and so on, and you have to sort of guess as to what should be the pattern you expect in the fifth square that is shown there. So, by looking into this pattern, you can say that alternately the L shaped symbol that you see at the left lower corner starts with the filled symbol, then it becomes unfilled, again filled, unfilled. So, the next one should be filled. That is what your reasoning is. And if you look into, there are at least 3 such squares that are with filled. One at the lower is a C or D, right. So, then you have to think of which one of them, and then you have to see that opposite corner also is a filled one, and with that reasoning you say that for possibly the C is the one that should come there, by some reasoning that you come up with and do that. So, this is by looking at the patterns you sort of predict. That is what called as hypothesis, and it could be true. So, the inductive reasoning is the process where a small observation is used to infer a larger theory, okay, without necessarily proving it. Give an example, evolution. So, evolution is something that happens over millions of years. So, it is impossible for any scientist to live through as many years to see the process and observe, document and say. So most often what you do is, these are looking at certain patterns, you come up with certain theory which you say as this is possibly happening. When you talk about the theory of natural selection is one such kind of theory that has come from inductive reasoning, which is very, very difficult to test real time, because evolution takes ages to sort of undergo changes. The other good example is the contribution from Darwin is the Darwinian finches. These are the kind of birds that were present in the island called Galapagos, and Darwin went there and observed them, and he came up with an idea that all of them have different beak shapes and size, and all of them should have evolved from one particular common species. So he sort of proposed the idea what is called as adaptive radiation, because you come to a new island, there is a different environment, you don't want to compete, there are different places you can get food and so on. So they evolve, they change depending on the habitat, the place they were dwelling, right? Seeing this is what the little text that is shown at the end, in the bottom of this particular slide, is the verbatim I copied from the book of Darwin, the Natural Selection. Seeing this gradation and diversity of structure in one small intimately related group of birds, one might, what he refers to the structure is the beak, okay, one might really fancy, meaning you can think of, imagine that from an original paucity of birds in the archipelago, one species had been taken and modified for different ends, meaning one particular species came and settled, and then they populated different parts, and then they gradually undergone some changes. Now you have distinct species. That was his theory. Now we know that that is not just theory. Now it is proven that indeed all these birds evolved from possibly a common ancestor with lot more scientific support, right? So that clearly tells you that inductive reasoning can help in science, and some of these hypotheses that we have, theories we have come from inductive reasoning. However, inductive reasoning can have its own limitations. I'll give you some examples. Again, these are borrowed from a very interesting link that is shown at the bottom of the slide. For more details, I would recommend that you go and read the original text. I have borrowed it from that particular link. For example, we are talking about the honeybee, which is shown on the right corner, top corner, which an insect which can sting you, right? This bee stung me, and you are a biologist, you are a zoologist, you know that it belongs to a group called Hymenopteron, okay? Then it's not a bee, you also have wasps, okay, that can also sting. So this wasp stung me, it's a Hymenopteron again. This fire ant stung me, is a different insect, again that belongs to the same group called Hymenopteron. So based on these three successive encounter with insects that stung me, which is painful event, I came to the conclusion that there's a pattern there. Three distinct species, all stung, all painful equally, all three insects belong to Hymenopteron group. So therefore I can say all Hymenopterans, or the insect that belong to this group, have stingers, meaning they can painful when they sting, right? So that is a pattern, that is a hypothesis theory I can make, but it can one needs to test. Let's look at some other example. For example, all apples are fruits, all fruits grow on tree, therefore all tree fruits are apples. Again, there are limitations, we will come back to that little later. Let's see this potential problem by looking at certain pattern and making certain theories or assumptions that could be wrong. Inductive leap, that's what called. Your generalization might not be correct every time. Darwin was right, time tested, but it may not be true for everything. For example, the many Hymenopterans, right, do not have stingers. For example, the ant that you look at, they don't have they don't sting like the bees, they can use their mandibles to bite you, they can only bite, right? So therefore, unless you take every insect that belong to the Hymenopteran species, put on your hand and see whether it can sting or not sting, it's not a good experiment. You are unable to confirm or really support your hypothesis that all Hymenopterans are stingers, right? Therefore, the limited pattern that you see, you cannot stretch it further unless you have done an exhaustive study, right? Let's look at the other examples. All apples are fruits, all fruits grow on tree, therefore all apples grow on tree is may not be the best way to explain that. It can't be that every fruit that you see in a fruit is an apple. So that is a limitation in that. So how do you really do? So this is what we explained, inductive reasoning. You observe, you find certain pattern, based on the pattern you evolve an hypothesis, and the hypothesis, if it is attractive, many suggest or support that, then it becomes a theory. Like for example, the natural selection. Now it is still a theory, but it is time tested, widely accepted, right? Now that is called as inductive reasoning. But there is a, for this to be true, you need to test, like what I said. All Hymenopterans are stingers. What you need to do, go and collect as many insects that belong to that group and then test whether they really sting. So that is what called as deductive reasoning. So you have a theory or a hypothesis. Hypothesis is that all Hymenopterans are stingers, and then you test it. So when you do a deductive reasoning, what is called as, you should test the hypothesis. You should be able to test the hypothesis and carry out some experiments. You observe, that is called observation, and the observations would confirm that your hypothesis was correct, and then you come up with what is called as deductive reasoning. Test existing theories and hypotheses, general ideas, by collecting experimental observations, specific examples that put those ideas into the test. That is called as deductive reasoning. So when you do this, anyone who repeat your experiment should be able to get almost similar observations. So that is what, when something is proven, the hypothesis become sort of law. For example, the theory of Mendel became, now you call as law of segregation, law of independent assortment. You call it as a law now, is because this has been tested many a times by many experimentalists, and you are able to predict what you would get, and you do get, right? That is what called as now deductive reasoning. So what you do? So all wasps have stingers. That's what we gave example, right? Oh, this is a general idea that inductively reached before, right? So this is certain minimal number of patterns with which you are able to generate an idea, and then you have to test. That is exactly what I have explained just now. So the results of your study may suggest further experiments. Always it happens. Remember I said that there is an infancy, you have a hypothesis, you do experiments, you get rapidly results, and then you sort of hit a plateau where you cannot go any further. Again you have to evolve hypothesis, take it further, right? So therefore always experiments lead to some observation which would demand further experiments, right? And therefore you have to go and do more experiments and take the research forward, right? That is precisely called as deductive reasoning. Most of the scientific discoveries are not all being carried out using the deductive reasoning. So in other words, induction is called as possibility. Inductive reasoning based on patterns, you suggest some possibilities, and the possibilities are tested by deductive reasoning, and then you say this is what the fact is. Like now you talk about genes being inherited from father to the next generation, mother to the next generation. You now know that it does happen, right? So but this is something that Mendel told much before anyone could think of. Therefore it was then called as hypothesis or theory. Now it is a law because it does happen, that becomes the truth. So that is how the science evolves. So let's see the difference between different definitions. You call hypothesis, you call theory, and you call law. So at times we change these statement, hypothesis into theory or theory into law and so on, but each one has got specific definition, and therefore when you say something you should know what you are saying is an hypothesis or a theory or a law, and as to why you should say so. Let's see first the hypothesis. Hypothesis is an explanation for an observed phenomenon. So you have observation, either you have made yourself or you find the literature that people have done experiments, they have these results. So based on the results, that is observation, you come up with an hypothesis, right? Explain what you expect to happen. You say that this is what it is. For example, this is a gene, and this gene is expressed when I am exposed to a given pathogen. Therefore, this gene, when it expresses, it protects me from the infection. Say, let's say this is a hypothesis. So if this is a hypothesis, then you expect something. What do you expect? If I am exposed to the pathogen, the gene should be expressing. So that is expectation. So therefore you can test that, and you can measure, is it really the expression level gone up? Is it really that the gene is turned on when I am infected with certain bug? And importantly, it can be proven wrong, because that is very important. My hypothesis may be absolutely wrong, may be attractive, but it is, when I test that, I will find that that is not possible. It's not happening. So what I do? I don't feel sorry. I go back, read more, think more, I come up with alternate hypothesis, which again can be tested. I do. That's why there is a lag period. When you have certain observations, then you have to identify alternate hypothesis, you have to do more experiments, and one of the hypotheses would give you a lead again, you take a quantum jump. So therefore, failure is not considered to be failure in that sense, because it helps you to move to an alternate hypothesis. Therefore, failure is as important as success in science. Let's see some of the examples, which now either are statement, again they have taken it from the link that is shown below. If you leave the lights on in the bedroom, then it will take longer time for people to fall asleep, right? It may sound like, oh, it's true, but let's say that, is it testable? It looks very attractive because the lights are on, I cannot close my eye, it is still, I could feel the sensation, therefore I don't sleep. If it is dark, I sleep, right? Therefore, I can test it. I can have two different rooms. In one, I can have the lights on, in other, I can turn off the light and see in which room people sleep early, right? Testable hypothesis. Then I can say, indeed, that is the case. If you store apples in a fridge, then they stay fresh longer, right? Then again, this is testable. To keep it outside and check it. If you keep the window curtains closed, then the AC would consume less electricity to cool the room. Now it would look like it is obvious, but it is obvious now because somebody has tested and shown that, they tell you, okay, put the curtain on, when you turn on the AC, keep the door closed, therefore it will consume less electricity, because now that is how it works, right? So that is how hypothesis becomes, help you to prove and become effective in day-to-day living as well. So now you go to the second, that is theory. So what is theory? A hypothesis that stood time, meaning at least nobody showed that the hypothesis is wrong. It may not be proven correct, but nobody has shown that it is not a good hypothesis. It is well substantiated in explanations. So many others have also done work, and then they are able to get data which again support a given hypothesis. Therefore, the hypothesis stayed for years. For example, when you talk about Darwin's contribution, the theory of natural selection is not something that one can test it in the lab. It is difficult, right? But now you have so many different observations that have come from multiple groups for over 100 years, then now that this is theory, whatever hypothesis that you proposed is very attractive, and still that is the only explanation that we can give. Therefore, it becomes a theory. It's an organized system of accepted knowledge. Everybody, vast majority of the practicing scientists, they say that that's the best thing and it's fitting into whatever observation you get, and this applies to in a variety of circumstances to explain a specific set of phenomena or observation. So therefore it becomes a theory. So that's the theory, but it is not proven yet, therefore it is not a law, but still an hypothesis that is time tested by a number of groups, well accepted, therefore it becomes a theory, like the theory of natural selection. That's something that I already told you. Let's go to the third one, that is called the law. What is law? This is not about the law that governs our civic society. It is about the law that sort of explains us many other scientific phenomena. A natural law is described by a sequence of events in nature that has been observed to occur without variation under the same conditions. So when you have the experimental conditions set, when you repeat this experiment, you know that this is what I am going to get. Okay? Over and over and again, you can do this experiment, you will get it, and as expected in a hypothesis, the end products are as expected, therefore it becomes a law. Natural law is the basis of experimental methods in science and is dependent upon cause and effect. So you can change the parameter, it will change. So then we can say what are the parameters that regulate. For example, you have enzyme, you have substrate, right? So there is a kinetics, there is a law for it. I don't want to tell you because most of you know that. So you know that if I increase the enzyme concentration, what is the end effect, right? So you can do this. That is what exactly explained in the law. When a hypothesis becomes repeatable with the variation that you bring in, and you expect this is what will happen and does happen, then you know it becomes a law. A natural law predicts that something will happen under certain set of circumstances, but it does not explain why it happens. Possible that it doesn't really explain why it happens, but it does explain that it will happen. Then you call it as law. The laws of thermodynamics, Mendel's law that we gave example, all these are to begin with hypothesis, but time tested, repeated, tested by many. Now you know all the parameters, you can predict and it will exactly will happen given the parameters are correct. Therefore now you call it as a law because invariably that will happen if the conditions are right. So this is what it is. You start with one or the other form of reasoning, inductive, deductive, then you have set of observations. Based on the observations you have an hypothesis. The hypothesis can be tested using experimental approach. If you test, and many other researchers tested for multiple times, various groups, different models, different conditions, and they are able to get exactly as predicted by the hypothesis, then it becomes a law. But there could be certain hypotheses which cannot be testable or cannot be tested, then, but still people do the experiments and that suggests that the hypothesis is correct. And then eventually the hypothesis over the time may become a theory, right? Still not proven, but that is the only way you can explain things. Therefore, it is likely that's what is happening. That is what is key theory. So for both these, you have hypothesis, something tested, found to be true, that becomes law. Something very convincing, something says that that is indeed the case, but you cannot prove it. That becomes theory, right? So these are the two different ways by which you look into that. So that is precisely the case, that you have a deductive reasoning, you have theory, you have hypothesis, then you do experiments, and then you get observations and confirmation. What is shown on the left side in the screen is the deductive reasoning. So when you do this is what you report. So when I come to scientific communication, you may be wondering why I am talking about all these things, because when you explain things, you need to tell that this was my hypothesis, and you have to say why your hypothesis could be correct, reasoning, right? And then you have to tell how I tested my hypothesis, and you have to tell what were your observations, and then finally you have to conclude that your observation indeed proved that your hypothesis is correct. So that is called as writing, scientific writing if you write a paper, or if you communicate like the way I do, you present your ideas, hypothesis and your observations, that becomes oral communication, then again it is called as communication. So this is how you introduce a topic that is shown on the right side, that you present your hypothesis based on certain assumptions, observations, and then you define the question, because you may not test in the hypothesis in as a whole, but you may take certain elements, And how do you test? You come up with study design. So you have certain models, and that you have certain parameters, and then that is what called as study design. And you conduct experiments, you have some observations, and the observations, based on that, you interpret something, and then you extrapolate what is called as discussion. So that is what called as communication. Therefore, you need to understand the philosophy behind science for you to really execute your experiments, and then to convey or communicate to the audience. So you need to understand the whole thing to be an effective communicator. So I'm coming back to the original slide that I started with in this week lecture, that you have performing artists. Some of them dance, some of them sing, some of them play music instruments, some of them don't do anything but paint, but some of them compose music, right? Talk about A.R. Rahman, what he does. He has to do many things. He is a music composer. What he does, he basically listens to the story of the movie, and he knows what are the characters, when a particular song should be brought in. So you should know the context, and then you express a particular mood, whether it is a mood is something that, two people met, they are very happy with each other, then you have a different kind of a mood, or they are separating, for example, then it's a different mood, or it is something else. So you have to bring out the music to express the emotion, so express the mood of that situation. Then you have to have that, the composition. Then you have to have script. Then you have to ask the script writer to write the make the script such that it fits into the mood. And then you have to have a singer who would sing so beautifully to express the happiness or sorrow or whatever. Again, it depends on the context. Then you have the orchestra, the musicians who gel with the rest of the thing, again conveying the same whatever particular information. So that's what it does, right? So basically, a music composer is somebody who uses so many other talents, like a singer, scriptwriter, musician, and so on. Plus you have what is called the art director, who have this song being played, and then you have all the characters, background and sound, music, light you bring in. Then even there are visual effects to add more strength to the whatever information that you would like to convey. So everything gels there to give you the feeling of whatever mood or scene that is there in a given movie, and that is what the film is about. As a researcher, you have to do the same thing like this. You are the only one person who have to do that. You have to read, get idea as to what has been done so far, and then you have to develop an hypothesis, develop methods, approaches, execute, carry out the experiments, document all the observations, and study your observations, write results, extrapolate, and then write, communicate, speak. You have to do everything. It is like this one-man band. You are Rahman, you are Lata Mangeshkar, you are Amitabh Bachchan, and you are everyone, So you have to do everything, including being M.F. Hussain, because you have to make figures, you have to make schematics to convey what you want to convey. In other words, you are just like any other performing artist if you want to communicate what you have done, in addition to what you have done. So you have to learn. All these people I'm showing in the screen are someone who born with maybe limited talent, but with dedication, they have the interest, they have learned, they mastered, and they did exceedingly well. And you have to do something like that to excel in science as well. It's a profession. It is not a hobby, because maybe it is begin with as something like a hobby for all these artists, but they become professional, and that is exactly what you call in science as well. To be an effective communicator, you have to be a professional. You should know how to communicate. For that, you should have understood what is science. That's what I discussed so far. I'm going to, in the rest of the lecture, I'm going to really talk about what really helps you to become an effective communicator. I'll give you some examples again. So you need to know what is a hypothesis. You have to define the questions. You have to address the questions by designing experiments, observe, interpret, discuss, everything on your own. You are a single man in a band, whatever called as, right? So therefore you have to do. So you have to learn everything. That is very, very important. And it's important because you have to tell the story, meaning what you observed, how good are your findings, right? These are very important. If you don't communicate, even you may have wonderful observations, a science may be path breaking, but unless you communicate, others cannot understand, they are not going to appreciate. It is just like storytelling. You must have seen this movie PK. It conveys at the end of the day, when you move out of the movie hall, you have a take home message. And that should be there whenever you communicate that, oh my God, this guy has done this and this is what his contribution. For that you have to have effective communication. Some movies do exceptionally well because the director put in a lot of effort to convey what really he had in his mind. It is very challenging. You have to bring in characters, you have to give life to the characters, you have to think about the surrounding, the dialogue, the sound, everything has to gel well to communicate what you want to communicate. If you don't do well, the movie will flop because audience don't like. You don't go again. You tell others it's not worth seeing. But if the movie is good, because you appreciated the story, because it has been told so beautifully, because it carries something that you are connected with and you are able to appreciate, then you tell others, hey, go and watch the movie. So that is how it becomes box office hit. So therefore it's important that you communicate well in every day, including your science. Only then people would appreciate. It is not that a movie that did not hit the box office, the director was not really eager to do a better job. He tried his best. Only thing, he could not be the best. So you have to be the best to communicate effectively as to what you have done. Otherwise your research will not be appreciated. You have examples again, right? There are movies that has huge investment. For example, the one that is shown on the left side, Bahubali, is a record movie in terms of the money spent in making a movie, because the story required that kind of settings to effectively communicate a story. Therefore you need all these things to tell that story. Therefore they invested. And it was so successful because they are able to communicate what they wished to, and people appreciated. Therefore, there was a revenue generation as well. On the right side, you have another movie, which is a low budget movie. Nothing. There were 3 characters or 4 characters, one a car. That's all that movie was about. Nothing was there. But still, the story was so effective, right? So it's not that how much you invest that makes a story successful or not, a movie successful or not. But how good you are able to communicate, how good you are able to tell the story is exactly the same thing in science as well. Your research may involve a lot of fancy equipment, a lot of money, grant, whatever it is, but still if you are unable to communicate, it may not really sell well. Or you may have a simple question which did not require any sophisticated equipment. Remember Susumu Ono's discoveries, just making chromosome, cutting the chromosome, weighing it, but still you could come up with discoveries that became laws, right? Like, for example, there was a paper that came in Nature from India which talked about how the Indian population evolved. It involved sequencing of multiple genes, huge experimental setup, lot of funding to come up with certain discovery, which is very, very fascinating. You could also have discoveries coming out in the very similar journal, but which had very little input in terms of money, very simple equipment, still you can make good story. So it's all about how you conceive ideas, okay? And then how do you come up with questions that are original, questions that are significant, how do you test the hypothesis, what observations that you have, and finally how good you are able to communicate, because you have to tell the editor that your discoveries are worth to be published in a high impact journal. Therefore they can read, they can understand. If you don't tell the story well, they are like you. When you go to a movie, you don't like a movie, you're going to go and say forget about it, don't go. The same thing editor will say, okay, it's worthless, reject. It doesn't go for review. Therefore, you should be able to communicate well, and this course is nothing but about making you understand some of the aspects as to how you can make an effective communication, and that is what called as the science of communication. We are coming back to the old slide to tell that scientific communication is exceedingly important, and from the next week onwards we are going to take examples and we are going to discuss as to how you can communicate better. With that, we will end the first week and we will see in the next week.